Okay, hello everybody. I think I hope you can hear me. This is Yasin, and I just shared the link to the material for today with you, and you can also see me. This is me. I'm a real person talking here. So I just shared the link with you guys. So I'm gonna share it one more time. You can get the material for today from this link. So I have one PDF file, and I also have another file, Jupyter Notebook. We are going to work on that Jupyter Notebook with you. So I'll guide the thing together. So we're gonna enter the code together with you. I also prepared an assignment for the second week. So the assignment, it's gonna be a simple assignment. I'm thinking to add one or two questions actually on the assignment. That's why I didn't share it with you now. And you can do the assignment yourself. And I think on next Saturday, you're gonna have another session with another instructor. So you can go through the assignment with the instructor during the TA session. So I just sent the link one more time, so you can just get the material from that link. Okay, so let's get started. By the way, I'm normally using my iPad for this part of the class, but somehow I cannot share my screen from iPad. So this is very strange. Normally it never happened, but last week it also happened too. Somehow I couldn't share my screen from iPad. So I'll use my computer. Today, we are going to actually continue from where we left last time. It's going to be about introduction to supervised learning. Just really quickly repeat a couple of things from last time. We said machine learning algorithms are divided into two main groups, actually, supervised and unsupervised learning. With supervised learning, we have the labels or the target values. And we also have, in addition to labels are Y, and then in addition to Y, we also have the feature set, which is X. So if we are trying to predict an individual's income, right? So income will be the target variable, and any extra information about this individual, say his age, his education level, the zip code he's living, his gender, his marital status, all that will be the feature set X. With supervised learning, what we do is we train a model, and we'll train models, you will see in a minute. We're going to train the models using the target variable. So given any individual's feature set, we also know his income. If we are trying to estimate individual's income, from the feature set and known target values, we are going to train a model so that later on, when someone gives us a new individual's feature set, like his income level, his zip code, his marital status, we are going to try to estimate his income. Right? This is supervised learning. With unsupervised learning, we don't have this information. We don't have the target variable information. Okay, so we said the simplest algorithm that we can start with is, we said, nearest neighbor. And by the way, I'm just looking at the, I just shared the link, so you can check the link from there. So the simplest algorithm that we can begin with is nearest neighbors. So what happens with nearest neighbors is, as you see on the screen, we have blue and red dots. These are pointing to the data points, right? These are data points. In this example, our data points have only two dimensions, right? Dimension 1 and dimension 2. You can call it dimension, the horizontal dimension and perpendicular dimension. So these data points have two dimensions, and also they are of two classes. So red class and blue class, right? So this is the representation of our, this is how we demonstrate our data points on the screen. So if you take this data point is of red class, and its perpendicular dimension takes value of -2.1, and its horizontal value takes, say, 0.3, right? So that is one single data point. So if when you are working on nearest neighbor algorithm, nearest neighbor algorithm is gonna first of all get trained. So you're gonna train the algorithm. Training the algorithm in this case means you just memorize your training data points. Your training data points are those data points that you know their labels. So when you are training models, you divide your data into two pieces, we said last time, train data points and test data points. For nearest neighbors, when you train the model, you are simply memorizing your data points. When it comes to estimating the class of new data points, in this case, you have 3 new data points. When it comes to estimating or predicting the class of these new data points, what happens with nearest neighbors, k equals 1, you don't see k equals 1 in here, but k means it's the hyperparameter. The hyperparameter means parameters of the model that you have to modify, tune up, so that you can increase the performance of the model. So for k equals 1 means to predict the class of any data point, you're going to check its nearest one neighbor. So let's focus on this data point here. What is the nearest single one neighbor, k equals 1? It is this one, which is blue. So we are estimating or predicting, we're predicting that this new data point of which the its class is we don't know yet, right? We are predicting that its class is blue. Same goes with this data point, and that this data point is the closest one is red. This one closest is blue. So we predict that this one belongs to red, this one belongs to blue, this one belongs to, again, blue class. So this is how nearest neighbor k equals 1 works. Again, we are dividing our data into train and test before we start training the model, right? And again, remember from last time, we said this is how we are doing k-neighbors classify with scikit-learn. And today we're gonna do some practice on this. And then your homework assignment is also regarding how you can run scikit-learn. Okay, so first of all, we are in this case splitting our data into two pieces, train and test. So X-train is our feature set for train data set, X-set is our feature set for test data set, and similarly, Y-train is our train set for target variable, and similarly for test variable, Y-test, for test set for Y-test. So this is our train and test data sets. The next thing is we are going to import the k-neighbors classifier class from neighbors module of scikit-learn. So scikit-learn has many modules, and one module is neighbors, called neighbors. This neighbors module includes classes. One of them is k-neighbors classifier. We also have k-neighbors regressor, right? So in this case, we want to work on k-neighbors classifier. So that's why we are importing k-neighbors classifier here. We are importing. Once we import this class, next thing is we are going to instantiate, we call it instantiate one object, one instance actually from this class, KNN. We can call it anything. We're gonna call it KNN. So when we instantiate this class, this instance, this object here, KNN, k-neighbors classifier, our algorithm is expecting how many neighbors, right? We're gonna be using for this algorithm. That this number of neighbors, n underscore neighbors, is the hyperparameter of the algorithm. In this case, we set it to 1 because in our figure, we were using k equals 1, right? So the moment you hit enter or you just run this line of the code, you now have an object called KNN. This KNN is coming with certain methods. Method is a function, right? Method means function. KNN is coming with certain methods and also attributes. And you can use those methods to start training your model. So for scikit-learn, the algorithms are coming with 3 main methods, right? Fit method, and then predict method, and then score method. So there are 3 methods. Of course, to train the model, the first method we're gonna be using is fit method. So KNN, as of now, is an object which is ready to be fit to your trained data set for number of neighbors equals 1. So what you're gonna do is you're gonna fit your KNN object by typing KNN.fit. You're gonna fit it to your trained data set. This is a supervised model, so you have X-trained feature set and Y-trained target variable. Once you run this line of code, and again, please give me, allow me to finish this part of the session, then we're gonna do this together here at Jupyter Notebook, right? So we're gonna do this part together, all right? Once you fit your model, the next thing is you can predict, because fitting means you trained a model. Using a trained model, you can predict what is the target variable for your test data set. As you see, when you predict, you need to put your Y test, right? Because we are predicting here your Y hat test, or I call it Y pred, right? So you're trying to predict for this X test feature set, what is the predicted target variable? That's what you're doing, right? So if you like, you can predict first, and then you can say knn.score. Or if you like, right after you fit, you can skip this prediction part. You can directly go ahead and then evaluate your model. What is evaluation? Evaluate your model. To evaluate your model, we are gonna be using score method. So knn, remember, is the object that you instantiated for k-neighbors classifier for k equals 1, right? Then you fit this object to your trained data set. Here you have a model that you already trained, right? So now you wonder how well this model is. So how can you evaluate this model? To evaluate this model, you can use score method, right? So when you say knn.score here, this method score, what it's gonna do is, of course, when you say .score, you need two inputs to the function here. One is your X test, which is your feature set for your test variable, test data set. And then the other one is the true target variables for this test data set. Why now we are included Y test here, but when we are predicting, we don't include Y test. When we predict, we don't need Y test. We are predicting Y test here, actually. Right? But when we are calculating the score for our model, we are including Y test, because that score is first going to predict the outcome for X test. Actually, that score is going to first run this part. Okay, so that score is going to first calculate Y pred, which is the predicted values for each row in your test data set. And then that score is going to compare this predicted target values with true target values. These are the true target values. These are the target values target variable values that you already had at the very beginning. So you are comparing Y test with Y pred, right? That's how you are calculating your score. So that's how you are evaluating your model, how well you are doing, right? So this thing, that score, is going to first predict target variables for X test, and then compare that predicted value with true Y test values, true target values. And then here we're simply printing, right? Print accuracy. This is just string, right? Accuracy will be printed on the screen, right? And then this curly brackets are placeholders. These curly brackets are holding place for what is to come inside this format thing. Right? Whatever is inside, this is going to generate a value. In this case, the value will be the accuracy. This value will be printed on the screen where it is marked by these curly brackets, right? Whatever the score coming from here, whatever the value that will be calculated or computed here will be printed on the screen in the place where these curly brackets are holding. And inside the curly brackets, what you see here is telling us that whatever the number coming from this score will be a decimal number with 2 digits after the decimal point. This 2 is pointing towards number of decimal points. This F is pointing towards the type of the number that will be printed. This number is of type float number, right? It's not an integer, it's a decimal number. Okay, again, we'll get back to this part in a minute, one more time. Then we said, what happens if we have, from time to time, I'm checking the questions and I'll try to answer as much as I can, but so many, so I cannot see the questions now. Okay, so what if we have more than one neighbors, right? So as I said, k number of neighbors is a hyperparameter. So you can set it to k equals 1 or k equals 3 or k equals 5. When you set it to k equals 1, we only have one nearest neighbor, and then these are the predicted classes. But when you increase k to 3, in this case, the predictions will change, right? You look at here, this guy was predicted as red. Now it is predicted as blue when we change k neighbors equals 3, because now we are looking at the nearest 3 neighbors, and based on the classes of these nearest 3 neighbors, we take the majority and then assign that majority class to this data point that we are trying to predict its class, right? So it was originally it was red when we are using k neighbors equals 1. When we use k neighbors equals 3, now the prediction changed to blue. So this is just to point that your hyperparameters are important in terms of improving or changing actually your model performance, right? So you have to tune up your model by changing your hyperparameter values. Okay, now let's look at the influence of number of neighbors. On the screen you have 4 plots for the same data points, for the same algorithm. Only difference is the number of neighbors is changing. The hyperparameter of the model is changing. We start from number of neighbors equals 1, then 5, then 10, then 30. Something you notice is, by the way, these are the boundaries separating blue from red, right? So one thing you notice as we increase number of neighbors is these boundaries are becoming more and more smooth, right? Smoother. See, the boundary is almost like a linear line. Actually, if you increase number of neighbors, it's going to become a linear line. But if you go back to number of neighbors 5 and 1, specifically for 1, you see that the boundaries are really, not following any pattern. But another thing you notice is all the data points, these are your training data points, all your training data points are in the right region. So if this guy is all alone by itself in the middle of blue region, but it still is in the right red region, right? So none of your training data points are actually misclassified. But as you increase your number of neighbors, look at number of neighbors equals 5. Now our guy here, which one, the lonely guy, is in the blue region. Another red guy is in the blue region, right? So we have now some misclassifications of our training data points. Right? By the way, how do we classify our training data points? After we train our model, we test our training data points too, right? So this guy, he's in the blue region because for number of neighbors equals 5, his nearest 5 neighbors are blue. Okay. So, and also the borders are becoming more smooth and then even smoother and even smoother. But now we have more and more number of training data points are appearing in the wrong region. So, as we change number of neighbors, our training data, our model for our training data set, its performance is changing. Okay, that's one thing we notice. Another thing we notice is as we change our number of neighbors, the region, the border separating these 2 regions is becoming smoother. Right? Actually, if you look at this first picture here, the borders actually, the separating these 2 regions are closely following the training data points. Right? It's almost like our model is fitting perfectly to our trained data set. Fitting perfectly to our trained data set. As we increase our number of neighbors, our model is less fitting to our training data point. Less fitting means we have some of our training data points appearing in the wrong region. Okay, just 1 second. Okay, you guys received the link to the material, right? So I already shared the material, so we can share it one more time in a minute. Okay, so let's continue. This phenomena that we just saw, what is that? that the same model for different values of the hyperparameter is performing differently, right? So in this case, for this specific model, when number of neighbors is 1, our model is fitting perfectly to our trained data set. As we increase number of neighbors, it's less fitting to our trained data set. And because it is less fitting to our trained data set, it becomes more general. More general means when we have new data points, right? So when we change number of neighbors or when we change our trained data point, this border will remain almost the same. Then we have new data points, right? So for these new data points that we want to predict their classes of, this border will not change for different training data points. It will not change significantly. Then we change some of these training data points. So we call this model complexity and training test scores versus model complexity. In this case, as we increase number of neighbors, our model becomes less and less complicated, right? Here, when I say complicated, I'm referring to my borders, right? So it's very hard to find such regions, such specific regions for data points. Here, the model is more complicated. Here, model is more simpler, right? Because the border is almost like a linear line. So if I had continued with this, I would have obtained a linear line, and I could easily tell you what that linear line is. The model is very simple. Here, it's very hard for me to define what are these borders, all right? So as our model gets more complicated, our model gets more complicated as we reduce number of neighbors, our training score accuracy is approaching to 1. And for this example, it's not very obvious, but our test score is going to be decreasing. We call this overfitting and underfitting. As your model complexity increasing, the accuracy, the performance of your model for your training data set, the model performance for your trained data set, as your model complexity is increasing, is going to increase. Right? As your model complexity is increasing, your model performance for your trained data set is going to increase. In our case, it's sounds a little bit counterintuitive, but our model complexity is increasing as our number of neighbors is decreasing, right? So when number of neighbors equals 1, we had the highest model complexity and highest score for our trained data set. However, as your model complexity increases, means as your model fits more and more to your trained data set, your model becomes less general, means this model will not work as well as it works for your trained data set. This model will not work for new data points that are not in your trained data set, will not work as good for these new data points. We call them test data points. As your model complexity increases and then fits more and more perfectly to your trained data set, that the same model will work or perform less, or poorer, right? For new data points, for your test data set. So if your model is operating in this region, if your model is operating in this region, which is doing perfectly for your trained data set, but it is performing poorly for your test data set, then you are overfitting your model. Okay. So our goal is we are going to reduce model complexity. We are going to sacrifice from model performance on your trained data set, but our main goal was actually not trained data set. Our main goal is creating a model general enough that is going to perform well on new data points, right? We are going to reduce our model complexity, make it more general. It can perform, give us a less accuracy on your trained data set, which is okay. But we want to find this point here, which is going to maximize, which is the maximum point, maximum accuracy for our test data set. Right? So again, this is the sweet spot that we are after. Now, if you reduce your model complexity even further, like in this case, increasing our number of neighbors, this line will become even more and more linear, and the model will become more and more general. If you make your model even more general, after a while, you will see that your score is even getting worse for your test data set as well. So if you're operating in this region, which is on the left of this sweet spot, then you are operating in the underfitting region. So when you train a model, you are going to tune up the hyperparameter value. You're going to change the hyperparameter value. If you see that when you change your hyperparameter value, both your train and test accuracy or train and test scores are improving, that means you are in the underfitting region. Okay, so you are changing your parameter values, and you see a huge gap between your train and test data set accuracies. That means you are overfitting your model. Okay, I mean, there are different ways of reducing overfitting, which we're gonna learn later. So in that case, by changing hyperparameter values or by introducing regularization to your model, which we're gonna talk about regularization, you're going to reduce the complexity of the model, try to catch this sweet spot. And it's not very easy, okay, to catch this sweet spot. It may not be very easy. You can skip this point. And then when your model has only one parameter and it's a simple model, it's easy, but for large, for example, neural networks, it may not be easy to catch this sweet spot. Okay, let me get to this line actually, because I didn't mention nearest centroid algorithm. Normally I was talking about it, but I just skipped it. That's why I skipped that slide here. So let's get back to our training set one more time. We have the feature set and we have the corresponding labels. As you remember, we are dividing our data set into two pieces, training data and test data set. Overfitting will happen on this part of the data set, the green part, right? And then how do we understand there is overfitting? The performance on this green part will be significantly better than the performance on the purple part, okay? And then you need to find a way to reduce the performance on the green part and increase the performance on the purple part. Okay, so another example, again, at the second part of the class, we are going to do this together, a similar example, not exactly this one. So let's see, let's look at this example here. This time we are using breast cancer data set. There are certain data sets, we call them toy data set, available from scikit-learn. Scikit-learn has a module called data sets. So this module includes certain data sets available for us to train our models or for learning purposes. So breast data set is one of them. And to load this breast cancer data set, we are importing load breast cancer, and then we are simply instantiating load breast cancer. Actually, what we do is now this data, okay, has data part and the target part as well. So data is it's like a dictionary. It has a key value and set of key values and target values. Two key values you see on the screen is data and target. And to have access to the values for these keywords, we are using data.data. So data is, this data part is referring to this one, this object here. Actually, it's a dictionary now. And dot data is the keyword. This dictionary has, if I'm not wrong, 6 keywords. Dot data is the data part, data value, and dot target is the target value. Okay. So X is our feature set, Y is our target variable. X is assigned to data.data, Y is assigned to data.target. So we have something here which we're gonna talk about later, but because it is here, I'm just gonna mention it, scale. So sometimes, and it's not sometimes actually, most of the time, we need to scale our data sets because our feature set is composed of columns, each column referring to a certain feature. For example, one feature may be talking about a measurement in terms of, let's say, meters in the range of hundreds. Another feature may be talking about some measurements in the range of, in the range of, 0 to 0.1, right? all the numbers are changing between 0 and 0.1. So one feature is taking values from 0 to 0.1. Another feature is taking values from 0 to 1 million, taking values from a very different ranges, right? In that case, if you are running an algorithm, specifically like an algorithm like k-neighbors, which is solely depending on distance metrics. So if one of your features is in thousands or millions and another feature is taking values from a very small range, your k-neighbor classifier will focus its attention on the feature with really high values. That feature with really high values will dominate the algorithm. So in that case, we are scaling our data set, means we are taking all our features and then we are taking all the values to the same range, let's say between 0 and 1. Okay. Regardless, the original feature might take values from millions, but when we scale it down, now the scaled feature will take values from between 0 and 1, right? So in that case, our k-neighbor classifier will work much better, much better, because now we are not allowing any feature to dominate the algorithm. Okay, so we see something different here. What we see something different here is I'm using split, train test split. Remember, train test split is a class from scikit-learn. It allows us to split our dataset into train and test datasets. This split, you can do it manually. It's not a difficult thing, but scikit-learn already lets you do this very simply, right? Train test split X and Y is gonna create two pieces. But here we are using train test split twice. Okay, see why this is happening. In the first time, when we create a split, so the first split, as you see, instead of saying train, I said train val. So this is I'm creating one piece and I call it train val. Actually, this is the piece where I'm gonna have my train and validation data set. The other split, the other part of the split is still remaining the same, X test. So this is my test data set. So I take my test data set, I put it aside, and I'm not gonna touch it until the very last moment. It's okay. I'm not gonna touch it. It's right there. I'm not even looking at it now. Okay. My test data set is separated. Now I'm gonna focus on my train validation data set. Now I take my train validation data set, and then I split my train validation data set one more time. Now I have my train data set, and I have a new piece, which I will call validation data set. Now I have three data sets. Test data set, which I already just put it aside. I'm not touching it. So it's right there. I have train data sets, and I have validation data set. Why did I come up with this new X validation? So again, going back to our k-neighbors classifier, remember number of neighbors is our hyperparameter, and we just saw that as I change my number of neighbors, my model performance is significantly changing. And I have a decision to make. I need to find, as I change my number of neighbors, I want to find this sweet spot. So to which number of neighbors this sweet spot corresponds? If my number of neighbors is 1, I'm right here. If my number of neighbors is 50, I'm right here. What value of number of neighbors? Is it 10? Is it 7? Is it 6? Which value corresponds to this sweet spot, right? That's what my job is now. I want to train my model. When I train my model, I want to decide on which number of neighbor is the best one, right? Which will give me the sweet spot. Okay, to do that, I need to train my model, and then I need to evaluate my model, check how well I'm doing. And then if I don't like the way the evaluation is telling me, I go back, change the hyperparameter value in my model, train my model again, and evaluate it one more time, train my model again. So I'm gonna go back and forth between train data set and some other data set that I need to test my data set. Now, to test my model, I will not use my X test data set. I already told you, right? X test data set is separated. It's right there sitting. I'm not gonna touch it. Why? If you go back and forth between your X test data set and your train data set, after a while, the model will be overfitting to your test data set as well. In that case, you are losing the The model will become, again, specific to your train and test data set. In other words, the model will be fitting perfect to your train and test data set, because you are going back and forth between train and test. By changing the model parameter, we are also trying to fit not only to your train data set, your model will be fitting perfectly to your test data set as well. You don't want this. You want your model be as general as possible. You want to test your model one last time before it is launched. That's why we put our test data set on the side. Then how am I going to go back and forth to see which number of neighbors is the best for me? For that, I'm creating this validation data set. So I'll be using this validation data set. It is already part of the train data set, actually. But now I separated my train and validation data set. Actually, I separate my train validation data set into two pieces: train data set and validation data set. On train data set, I'm going to train my model. On the validation data set, I'm going to evaluate my model for that specific number of neighbors. If I don't like it, I go back to my train data set, change my number of neighbors, fit it again, come back to my validation data set, evaluate my model, see how it does, and then I'll go back and forth to decide on the value for my number of neighbors. Once I make that decision, I'm going to test one more time on my test data set. Then I will launch my model. If I do, really bad on my test data set, that means my model is not working really good, right? So that's not very desirable. But we're not going to be using our test data sets frequently. Okay, that's the lesson actually here. Okay, so let me just quickly look at if there are anything that. Yeah, there are a lot of questions coming. It's very difficult to answer all the questions. I'm sorry, but yeah, we are going to go through a loop to determine the sweet spots, scaling the data sets. In this case, it's going to reduce the values. There are different scaling. There are different ways we can scale. Some of them will allow us to bring the values from between 0 and 1. Some of them will be mainly between -1 and 1. So we're going to learn about scaling. Scaling is your features in your data set might be taking values from really different ranges. For example, age feature will take values from 0 to 100, right? Hopefully all of you guys will live more than 100 years. But on average, right, it's going to be between 0 and 100, let's say 110. But income, or income, if it's a feature, income will take values from hopefully like 40,000 to 200K, for example. So one feature is only taking values from 0 to 100. The other one is taking values from 40,000 to 200,000. So those two features are taking values from very different ranges. And then when you implement K-neighbors classifier on this data set, the feature set which is taking values from thousands will dominate the algorithm. Why? Because K-neighbors classifier, it's measuring the distance between each and every data point. And distance is going to be measured based on all features. So imagine that you are measuring the distance on the feature which is taking very small values. That distance will be really, really small. And then you are measuring the distance that will be taking the values from thousands, range of thousands. That distance will be really big. And of course, the feature taking values from thousands will dominate the distance metric, right? Okay. So let me continue. So this is an example on the impact of training your model so many times. So if you train your model so many times, it is more likely that your model is going to overfit your training data set. If you force your model really hard, your model is going to do everything to fit to your training data set. Okay, so let's look at this example here. So in this example, we are running a for loop for 1,000 times. So when you say range 1,000, what you are doing is you are creating a list of numbers from 0 to 999. Okay, list of numbers from 0 to 999. And I right, is going to take values from 0 to 999 sequentially, one by one. So I will be first 0, then will be 1, then will be 2, then will be 3. So you'll be running this whole thing 1,000 times, 0 to 999, 1,000 times. And you notice this indentation here, right? With Python, when you're running for loop, each cycle of the loop will be executed through this block of code indented, right? Okay. Okay. So as you see here, I had two empty lists, val and tests. That one will be validation data set, the other one will be test data set. Okay. What am I doing here? What I'm doing here is, for each time I'm executing this loop, I am instantiating a random variable. It's a random object, RNG, for a certain seed value. So let's not get into it for now. So basically what I'm doing is so the computer gives me a sequence of random numbers, for each seed value. If seed value is 0, there is a certain sequence of random numbers. Every time you use the same seed, you're going to be using the same sequence of random numbers. Right? So 1,000 times I will be running this loop, and for each time, I'm going to generate a random object. And from this object, I will be generating random numbers of size trained data set. So what I'm doing here is, earlier I created this trained data set here, right? This trained data set here. I use that trained data set, okay? But I'm gonna add, with my trained data set, I'm gonna add my trained data set with some noise. So why? For each cycle of the loop, I'm generating a different version of my trained data set, okay? So my goal here is to let you know that when I'm running this 1,000 times this loop, I'm not even using the same data set, okay? I'm using each time a different data set. My trained data set is changed slightly different because I'm adding noise, a random noise to my trained data set. In other words, for each loop, for each cycle, I'm changing my trained data set slightly by adding noise. That's the point, okay? For adding that random noise. Okay, what is this? This is my k-neighbors classifier for number of neighbors equals 5. Okay, here I'm fitting my classifier to my trained data set, and this is my target value. Target value is not changing. I'm just trying to make a point here. I'm just changing my trained data set slightly by adding some random noise, and then I am checking my score for my validation data set, not even my trained data set, checking my score for validation data set, and I'm checking my score for test data set. You see, I didn't change my validation data set. I changed my trained data set by some random noise, and I did this 1,000 times. I trained my model 1,000 times on my trained data set, and each time I changed my trained data set slightly. After I fit my model on my trained data set, I tested my trained data set on my validation data set, and then on my test data set. And then I just kept the score, okay? I just kept the score for validation and test data set inside this list here. What do you see here? My validation score is 100%. What happened here? What happened here is, just imagine this. There is this model, and then I ran this model 1,000 times. Okay, 1,000 times. I trained this model 1,000 times. At least one of the times, or out of this 1,000, at least once, this model performed perfectly on my validation data set, at least once. So this doesn't mean that I found the perfect model. Out of these 1,000 models that I created, one of them happens to be perfectly fitting to my validation data set. Now, because it is fitting perfect to my validation data set, right? I picked that model, which is perfectly fitting to my validation data set, and then I tested that model on my test data set. its performance is 0.958. Okay. My point here is, if you train your model enough number of times, if you train your model so many times, it is highly possible that you're going to find a model that is working almost perfectly for your, even for your validation data set. Now, going back to test data set, I told you you need to put your test data set aside and don't touch it, right? So here, imagine that you did not do that, right? Imagine that you were using your test data set in the place of validation data set, right? Imagine that you were using your test data set in the place of validation data set to decide which model to use, right? That's what we call it information leakage, right? If I had trained my model 1,000 times and I tested my model 1,000 times on my test data set, in one of these 1,000 times, my test data set will give me the perfect score. Then I would think that, oh, my model is working perfectly, which is not the case. Right? So this is called overfitting. If you train your model so many times, it's going to be overfitting. So that's why we have this threefold split. We have a trained data set, we have a validation data set, and we have a test data set. And we are going to keep this test data set aside. We'll use validation data set for parameter, hyperparameter tuning. Now, we can implement this. Just 1 second, let me see if the message is soon. We are going to come back to scaling. So I'll talk about scaling later in more detail. Okay. Again, this means this guy means I'm receiving question on this one. This guy means this is a placeholder. This guy is referring to whatever value will come from here. It's a placeholder. This whole thing is string. This whole thing is string, which will be printed on your screen. This is a placeholder between the curly brackets. F says whatever the value is coming from here, its type will be a float number. It's going to be a decimal number. 3 means that decimal number after the decimal digit will have 3 decimal digits. That's all. Okay. So what is happening here? Let's look at what's happening here. By the way, I'm going to stop in 5 minutes. I'll give a break in 5 minutes. And then I'm going to stop at the next session will stop after 50 minutes because I have a meeting. So I have to get prepared for the next 10 minutes. Okay. So here is my threefold splits. I'm creating train, validation, and test data sets. Okay. Here is my test data set. Here's my validation. Here is my train. So what's happening here? This time, what I'm gonna do is I'm gonna be looking for the best number of neighbors. Is it 1? Is it 3? Is it 5? I'm using odd numbers because remember, nearest neighbors, if it is even numbers, I'm taking a majority vote. If it is even numbers, from time to time, I may have equal votes, right? In order to avoid that, I'm using odd numbers for number of neighbors. Okay, so I'm creating an empty list here. Later, I will append this list. This is the number of neighbors. I'm creating an array which is taking values between 1 and 15, and then step size is 2. So it's going to start with 1, then 3, then 5, then 7. Right? Here I am creating a loop. This loop is going to go through number of neighbors. Remember, neighbors is now an array of numbers, 1, 3, 5, 7, 9, 11, 13. Right? So I will be instantiating my model, k-neighbors classifier, for different number of neighbors. So it can be number of neighbors equals 1, can be 3, can be 5. And for this different number of neighbors, I am fitting my model to my trained data set. And then I am testing my model on I'm testing my model on my validation data set. And then I keep the score for this validation data set inside this list. which was empty originally, which is empty here, but I will append the score that I will get for my validation data set for this number of neighbor value. Okay, so this way I'll go through all the neighbor values, and for each neighbor value I will fit my model and I will compute the score for that number of neighbors on my validation data set. Okay, so now this val underscore scores, this guy, which was empty at the beginning, now it is a list of scores. Each score corresponds to a different number of neighbors. The first score will be number of neighbors equals 1. The second score will be number of neighbors equals 3. The third number of neighbors equals 5. Okay, so one of these scores is the best, right? One of these scores will be best. So let's say the third score is the best. In that case, I'm going to take this val underscore scores list. I'm going to take the maximum of these scores, and whatever that maximum score, what if it is the first one or the second one or third, if it is the third one, that means number of neighbors equals 5 is the best hyperparameter value for my model. Right? So this is what's happening here. I'm picking this is a variable that I just came up, best n number. This is a variable that's going to be holding the position of the highest score in my validation scores list. This guy here, this guy here, okay, it's going to return the index of the best score in my val underscore scores list. Val underscore score is a list, and p.argmax, the maximum arguments position. If it's the third one, if it's the fifth one, if it's the second one, we don't know. Whatever the position of that maximum value in that list, okay, then I'll take that position, that index, and then I'll pick from my neighbors, which it's a list now. Neighbors is a list of neighbor values. So whatever that position, if it's the third one, then the third neighbor, which is 5, will be the best value for my hyperparameter. Once I get this best value, okay, what I'm gonna do is I'm gonna go back to my classifier. I will retrain. First of all, I will instantiate my model for that best value of hyperparameter, which is, I don't know in this case, oh, it is 11. It is 11. I will initiate my KNN object for this number of neighbors. And then I'm going to fit it to my train validation data set, this whole thing, because now this is my train data set. And then I'm going to take the score for this KNN object, which was instantiated for the best number of neighbors. I will take the score of this model on my test data set. As you see, my test data set, I use it at the very last. So this is my best validation score. This is my best number of neighbors. This is my test score. See, there is some difference between test score and validation score. This might be an indication of overfitting. Okay. All right. Let me stop here for 5 minutes. Then I'll come back. I couldn't finish again. Let me see. Oh, just 1 second. I think I'm almost there. So I'll quickly go through the remaining of the slides, and then I'll do some exercise with you guys on this file. Okay. So let's stop for 5 minutes, and then I'll be back in 5 minutes. Yeah, I just saw a question right. I was leaving. I just saw a question. The question was asking why we are fitting our model after we found the best neighbor value, right? So after we found the best neighbor value, why we are fitting our model for that best neighbor value? Why we are fitting our model to our train validation data set, but not just train data set? The reason is we already have our test data set separated, right? And the rest of the data set that we have, train validation altogether, it's for training purposes, right? The reason why I had train and validation was because I wanted to find the best hyperparameter value by going back and forth between train and validation dataset. Once I find that best hyperparameter value, I don't need validation anymore. So again, validation and train together, they are my train dataset together, because that's the logic, right? At the very beginning, train validation is my whole train dataset, but I'm splitting my train dataset into train and validation datasets just to find the best hyperparameter value. Once I find the best hyperparameter value, now I go back, zoom out, and then train my model one last time on the entire dataset that I have other than my test dataset. If you have really a large number of data points, right? I mean, you may not do this. You may simply train it on your train dataset, but it's always nice to train your model on as many data points as you can find, because this will reduce the overfitting possibility. Okay, so one way to reduce overfitting is increase your training dataset size, right? Because as you increase your training dataset, you become closer and closer to the general case, right? So then I mean, your model will, if it is overfitting to the general case, which is the desired, right? Okay, so this is actually, this is called this is threefold splitting. Again, train, validation, and test dataset. But we may not have always the luxury of having really large data sets. That's one thing. And second thing is here, what we are doing is, when we split our train validation into train and test dataset, train and validation dataset, we are using the same validation dataset to actually almost test the model, right? Same validation dataset to test the model. So because of that, what we do is we come up with cross-validation. So what is cross-validation? Again, this is my let's go to this question. This is better. This looks better. So this is my entire data set. Let me also get rid of this picture. Yeah, this is my entire data set. I divide my data set into two pieces first: test data set and train. As you see, I just put my test data set aside. I don't touch it. I take my whole train data set and then I divide it into pieces. Let's call each piece fold. That's why it is called K-fold. K refers to number of folds. In this case, K is 5. Okay, I divide my train data into, in this case, 5 pieces, 5 folds. Then what I do is, now I'm going to take the first fold, and then I'll assign this as my validation data set, and I'll take the rest as my train data set. So I'll train my model here, and then validate or evaluate my model on this fold. Next, the same model, this time, I'm gonna train the same model on fold 1, 3, 4, and 5, and then evaluate it on this fold. Now, earlier, sorry for jumping back and forth, earlier, here, for each number of neighbors, I was evaluating my model on the same validation data set. And only once, I was doing this only once, right? For each number of neighbors, I was fitting my model here, and then I was evaluating this model on the same validation data set only once. But here, again, for say number of neighbors equals 3, I instantiate a model for number of neighbors equals 3. So I have one model. And then I'm going to test this same model. I'm going to train this model first on this green part, and then evaluate it on this blue part. And then I'm going to fit the same model on this green part. But this time, as you see, green part, most of the green part remains the same. But a little bit. So your train data set from one split to another is changing a little bit. But your validation data set is each time different. In other words, the same model, say number of neighbors equals 3, that is one model. The same model will be evaluated on different data points as you move from one split to another, each split, you are going to have a different fold as your validation data set. By the way, you're not changing the folds. You divide your data into 5 folds. Those folds remain the same. You are changing which fold will be the evaluation data set in the next split. So the same model will be, in this case, trained and evaluated, in this case, 5 times. So here, we had multiple models. Let's say we had, I think, 7 models. And then each model was evaluated only once. If we had run the same thing over this K fold, because K equals 5, then we had 7 models. Each model corresponds to a specific number of neighbors. Each of these number of neighbors would be trained and evaluated 5 times. Okay, that is cross-validation. So cross-validation is going to give even a better idea about how well your model is working, and then how much overfitting is happening, whether there is overfitting, is happening. So basically, you are creating, instead of having 7 models, in this case, you'll be having 35 models, right? Let's do the cross-validation here. Okay, now as you see, this time I'm not doing split twice, because this split, the second split, will be happening itself inside cross-val score. So scikit-learn is providing a model selection module. From model selection module, I have this class called cross-val score. So cross-validation score is actually doing this split. And then for each split, it's doing this fit, score, append. So these 3, actually 1, 2, 3, 4, these 4 steps happening inside, and also this splitting happening inside this cross-val score. Okay, I'm repeating, not this step, fitting, scoring, and appending. Okay, these 3 steps plus folding is happening inside cross-val score. So let's see what's happening here. I am again creating an empty list. This time I split my data into train and test. I instantiate my model for a specific number of neighbors. So neighbors can be from 1, 3, 5 from a list. For that specific KNN instant, I'm gonna this time instantiate my cross-validation. I'm gonna instantiate an instance from my cross-validation score. The first parameter is my estimator, KNN. Then I will put my train data set. So this train data set will be split into K folds. What is K? 5. What is K here? 10. This is CV equals 10 means I'm going to split my train data set and also Y train into 10 pieces. That's what it means, okay? And then for each piece, I will be running fitting KNN for each piece. So basically, scores will be returning 10 scores, 1 score for each model corresponding to a specific fold, a specific split for this number of neighbors. Next, look at this one. MP is referring to NumPy. Mean is one function, one method coming with NumPy, which finds the mean of the group of numbers. Remember, I told you scores is, in this case, returning a list of 10 scores. Each score corresponds to a split like this. So you train your model on folds 2 through 5, and then evaluate it on fold 1. This returns a score. You have 10 scores for a specific number of neighbors. And then you take the mean of these 10 scores. You are appending this mean to this list. So as you go through number of neighbors, for each neighbor number, you are creating 10 scores and taking the mean of these 10 scores and then keeping it in this list. So this way, you are doing the same thing. You are trying to find which number of neighbors this time gives you the best mean score. Okay, so it gives you a better confidence, right? So instead of focusing on a single model for the same number of neighbors, this time you have 10 models. And then you take the mean of these 10 models, and then you decide which number of neighbors is the best for you. Right? As you see, best cross-validation score is 0.967. And this is your test score, 0.965. Earlier, your best score was 0.99. And I told you, remember, this indicates an overfitting. With cross-validation, you are reducing the chance of overfitting because for each number of neighbors, you are creating 10 models. So this gives a better picture of how well your model is doing for that specific number of neighbors. By chance, your number of neighbors equals 3 might be giving you the best score earlier. But now the chance is reduced. Right? Now, for number of neighbors equals 3, you're gonna test your number of neighbors equals 3 10 times, not only once. Once it might have given you the best value, but when you test it for 10 times, so you have 9 additional scores, and you take the mean of that, that reduces the possibility of overfitting. So that's all about cross-validation. All right, so here how we are using cross-validation. This is data sets. We divide into test and training data sets. These are our hyperparameters, in this case, number of neighbors. We are going to cross-validate our trained data set, and then we're gonna find the best parameter. We've given this best parameter, we're gonna retrain our training data set, and we're gonna make this final evaluation on our test data set for this retrained model with the best parameter. Okay, I'm just worried that I will not have enough time for the practice session. This split, this split can happen in different ways. So there are different ways. I'm just gonna talk about 2 of them. One is, I'm just gonna focus on one of them, stratified k-fold. So k-fold is the k-fold, we just learned about it. This is k-fold. Stratified k-fold is, we are using this specifically for classification cases, right? When our target variable is taking values from categories. Okay, let's say your target variable is group of students, right? Whether the students are freshmen or sophomore or junior or senior. There are 4 groups, right? Freshman, sophomore, junior, or senior, right? And then you want to create these splits. You want to create these splits, right? So this is your trained data set. So you want to create this. So, and then when you split your X feature set, you're also splitting the corresponding Y, right? The target variable. Now, if your target variable is taking categorical values, like freshman, sophomore, junior, and senior, you want to have each fold represent the distribution of these 4 categories equally, right? So when I say equally, each fold will be representing the distribution of these 4 categories in your trained data set. So you don't want fold 1 be only freshman and fold 2 be only sophomore. If that is the case, if that happens, right, then your model is gonna be trained for a specific class, right? So if in your trained data set you don't have any junior, all your juniors somehow were in fold 1. In that case, your model will be trained only for excluding juniors. Juniors are in fold 1, only for freshmen, sophomore, and seniors. And then you're testing your model on juniors, which were not represented in your trained data set. You don't want this. You want each fold representing the proportion of the categories in your trained data set. Okay. So for that purpose, when we split, we are using stratified cross-validation. When we split our data set, so if these are the splits, and then if they are corresponding to different classes, like class 0, class 1, and class 2, so we want each of these splits take, for example, class 0 will be represented as much as it is represented in the whole trained data set. Okay, that is the purpose of stratified k-fold. When we are splitting time series data set, time series is a different animal. When we are splitting time series data set, we are not going to split randomly, because time series data set is following a sequence, right? So yesterday's data is very different than 3 months before's data, right? So it's important that we keep the sequential format of time series data set. So today's, whatever is happening today is more related to yesterday than it is related to 3 months ago. So that's why when we are splitting data sets, we are keeping the time relationship across the data points. So that's why we are not randomly splitting. When we are doing cross-validation on time series data sets, we are taking, for example, the nearest data points as one fold and others as the other fold of the trained data set. Okay, let me talk about grid search quickly and then jump to the Jupyter Notebook. Okay, so far we already talked about cross-validation. Cross-validation helps us reduce the possibility of overfitting. When we are doing cross-validation, we manually change the hyperparameter value, right? Remember, for k neighbors equals 1, and then 3, and then 5. So we first started with manually splitting our data set. Then we took care of that manual splitting part. We introduced cross-validation score. Now we are only changing the hyperparameter value. What if I also automatically change hyperparameter value? So and then cross-validation score is already happening automatically. Everything is happening automatically. I don't need to manually change things. So for that purpose, scikit-learn is providing this grid search CV. CV is referring to cross-validation. Grid search is referring to searching for the best hyperparameter. Okay. So what is this? I'm just going to talk about it in a minute. Let me see if some general questions that I can answer. Okay, for past weeks, I realized past week's material, the link was removed. I'm syncing my Google Drive. That's why probably the link was, I don't know. So I will share the link for the past week's material. No worries about it, okay? So let's look at grid search. Okay, again, I start from my train and test splits. As you see, even when you are creating your split for train and test data set, if your target variable is categorical, you can do this stratification on your train test split as well. Actually, you should do it, okay? So you are creating this split on your test and train data set. When you are splitting your test and train data set, you are also trying to keep the same ratio of categories that you see on your entire data set. Okay. All right. Now, let me begin from here. Let's look at this line here. Now I have a new thing, grid search CV. So this is grid search CV class. Grid search CV, as similar to cross-validation score, takes as the first argument, takes the estimator. In this case, my k-neighbors classifier. Now you notice something here, right? I didn't mention any hyperparameter here. Earlier, when I was running cross-validation score, this is my estimator KNN, which was instantiated for a specific number of neighbors. Now with grid search, I don't need to do that. I just put my, I just put my estimator inside grid search. The reason is the hyperparameter is coming here from here. So the k-neighbors classifier will be receiving different hyperparameter values from this parameter, param_grid. Param_grid is the name of the parameter, and this param_grid is the argument that I'm passing, which is coming from here. Now let me talk about this one. This guy is a dictionary. Okay, for those, again, I have a very different, people come from very different levels of Python. So some people already know, some people don't know much, or very new, let's say very new. So that's why I'm sometimes getting into details. This is a dictionary. A dictionary has a keyword and has the corresponding value to that keyword. And dictionary with Python begins and ends with a curly bracket. So I introduce my parameters, grid parameters, to my grid search with a dictionary. Later, we're going to see that I can change multiple parameters with one grid search. Okay, here I'm only changing one parameter. So what is the name of the parameter that I will be changing? It is number of neighbors. That is the name of the parameter that I will be tuning. I mean, I'll be tuning my model by changing the value for this parameter. And these are the values that this parameter will be taking. It's very similar to what we did here. Sorry. Here, right? Where's this? Here. Earlier, when I was doing, when I was trying to find the best neighbor value, I created my neighbors as a NumPy array, taking values from 1 to 15 with step size of 2. Like I'm skipping every other value, right? So that's what I'm doing here, right? The same thing. Number of neighbors is taking values from 1 to 15 with step size of 2. And this CV is corresponding to cross-validation, k-fold. In this case, it is 10. I'm going to come back to this later again. Okay, now this grid is a strange thing, okay? It acts like an estimator. It comes with its own methods, very similar to the methods that we have for estimators. Look, once I instantiate grids, I can fit grid to my trained data set. What happens when I do this? When I do this, okay, what happens is grid is going to take my trained data set, divide it into 10 folds. For each fold, it's going to fit k-neighbors classifier for each value of the parameter value, in this case, neighbor. So now I am creating 10 times the length of param grid, how many parameter values you are changing, whatever it is. If it's 7, I'm creating 70 models. Okay, 70 models. And then grid is going to return you best score, best parameter. And on top of that, you can even score your grid. You can even take the score of your grid on your test data. When you say grid.score, grid is going to find the best parameter, and then it's going to train your model on this best parameter, and then it's going to predict your y-test hat for this best parameter, and then it's going to calculate the score for this best parameter by comparing y-test with y-test hat. So all that is happening when we call grid.score. All right. So if you would like to see what actually grid is returning to you, so there is one attribute of grid called CV_results_. Okay. So, and then you can turn this into a data frame. And then this data frame now is holding everything happening when you're on the grids. So this is the list of everything happening, okay? So what your grid is doing is it's giving you mean fit time, mean score time, mean test score, all these different parameters, and all the test scores and train scores for each split. All that is available as the output of your grid search. So you can get into details of your grid search and do how your model was doing for different splits, for test score, for train score. Okay. And then as you change your number of parameters, you can see how your mean train score and mean test score is doing. So this shadow is telling you it's actually 2 standard deviation up and down the mean, okay? So remember, for each parameter value, you are obtaining 10 scores because CV equals 10. So this value here is the mean of those scores for 2. This is 2 standard deviations up from that mean and 2 standard deviations down from that, or 1 standard deviation, I don't remember now. But this tells you how your scores for this specific parameter value is actually distributed. Okay. All right, so let me switch to my Jupyter notebook, and I put some notes here for you. I got these notes, I didn't type these notes myself. I got these notes from scikit-learn's website. I'm pretty sure I put the links for that. If you want to read more, you can just click on those links. I remember. Yeah, I posted the links. Okay, so let's get started with this example. Before I get started, let me see if there are any common questions so I can quickly refer to or ask. So, yeah, I already shared this week's link, and then you can use that Jupyter notebook in that link, okay? There's one question about cross-validation. We are fitting, when we are creating, using cross-validation with CV equals 10, we are actually fitting, we are actually fitting the same model to each of these splits. So basically, we are training 10 models, but the model itself has only one hyperparameter value. Let's say for k neighbors equals 3, I take this model, and then I fit this model, I train this model 10 times, 1 for each split, okay? All right, so let's get started with this. Are there any other questions? Yeah, the file is right there. Okay, so you can use Jupyter Notebook or Google Colab. I'm using Jupyter Notebook when I'm teaching. I mean, it's more convenient for me. Okay, all right. So I'm gonna just import the necessary libraries here. I'll be using matplotlib to plot some of the things which you will see in a minute. So this PLT is an abbreviation for whatever you're importing. So whenever you want to refer to this whole thing, you can simply use PLT to refer this whole thing. Again, NumPy is another library that we are importing, and we are using MP to refer to NumPy. You don't have to use as MP. You can always use NumPy when you are referring to, but MP is, by convention, people are using MP as an abbreviation, so I'll be using that. So I'm just going to add, I'm using Jupyter Lab. I'm just going to add a cell under this step 2 so that I can type my code. So I'm going to import one of the toy data sets, digits from scikit-learn. That's what I'm going to be working on. Okay, I'm just going to import it. To import it, first of all, I'm going to let you guys know where I am importing this. Okay, from scikit-learn data sets. Okay, this is the module where data sets are kept. I will be importing. I will stop in 20 minutes. I'm just letting you know. Okay, I will be importing this load digits. Sorry. Okay, I'll be importing load digits. So let's import it, and then I will assign it to a variable called digits, load digits, and then treat this as a function. Okay, treat this as a function. So I am, let me run this first. And then I am importing this. So scikit-learn, when you import data sets from scikit-learn, they come like dictionaries, okay? So I'm just going to, this digits is now holding that dictionary. I'm just going to print the keys of that dictionary so that you see what you're importing, okay? So these are the things that we imported. data and target. Remember from our discussion. My God, where was it? Yeah, data and target. That's what I'm referring to, okay? Data and target. If you like, you can, this whole thing is coming as a data frame. If you like, you can use a data frame. These are the feature names of your data. This is the target names of your target. If, in this case, we have images, those images are stored in as images here, and this is the description about your data set. We're gonna be using images shortly, okay? Okay, so these are my targets. Let's see what is, sorry, what is the shape of my data sets. So if you want to have access to values corresponding to this keyword data, all you have to do is type the digits name and then type dot data. Now you are having access to data, and then let me see how many data points I have. Okay, I have 1797 data points and 64 features. So each of these guys are actually corresponding to a handwritten digit. This is a scaled down version of MNIST dataset. We have 10 classes. Let's see. We have 10 classes. I'm just going to, you see, NP is this one. Bin count of my target variable. And then if you like, you can also look at the length of this. Right? So I have 10 classes in my target variable because there are 10 digits, 0, 1, 2, 3. These are handwritten digits. And then each image is 8 by 8 pixel. And each pixel is represented by an integer from 0 to 16. Originally, the images are from 0 to 255, but that's another story, okay? Each pixel value is from taking values from 0 to 16, and I have 8 by 8 image. That's why each of these observations is 1 digit, and each digit takes 64 values, 8 by 8, 64. And each digit has its corresponding target, and target, I have more or less 180 of each digit in my data set. So 178 zeros, 182 ones, 177 twos, so on and so forth. Okay. Now let's divide our data set into the train and the test data sets. Okay. Let's do it. To do that, I need to import from scikit-learn model selection. Right. I need to import train, test, split. Okay. And then I'm just going to split my data set into okay. So what am I splitting? Equals train, test, split. Okay. I'm splitting my data and target together. Okay. Do not split just data. You're splitting data and target together. So digits. If you like, you can assign X equals digits data, Y equals, you can do that. Digits data, digits target. Okay. If you like, you can even say stratify equals digits targets. Okay. And then I'm going to use random state 0 so that we all will have the same results. Random state 0 means this random split will happen the same way for all of us. Okay. Because we are going to be using the same random sequence of random numbers. this stratification, remember, I want to keep the ratio of digits in my, both on my train and test data set same. Okay, let's run this. Okay, now I split my data sets. Let's check my X-train dataset shape. Okay, now it is reduced. By default, it is at 75-25 split. Let's also check the bin count for train datasets. You see, more or less, I have the same number of classes, right? Because I used stratification. Okay. All right. If you want to know what are the data points, let's see how they look like. I'm just going to print only one of the digits. So this is how your data points look like. Okay. They're taking values from 0 to 16. If it is 0, this pixel corresponds to black. If it is 16, it corresponds to white. It's in the image, this is 0, this is black, and this is white. It's a grayscale image. Okay. Now let's print this image just to see. I'm going to print the same, this data one. Okay. I'm going to print it the same thing. Okay. So for that, I will be using PLT. What is PLT? I already imported it. This is for plotting purposes. Okay, this is the library for plotting. So this class is PLT class. I will use print a grayscale image. Okay, and then I am going to show, this is just to show the picture. Which one? Digits dot. Now I'm not gonna say digits dot data. So this guy here is this guy here is to show the image, right? To show an image. Remember, we already imported the images. So I'll be plotting this image, okay? So digits dot images. So digits dot image, I have access to images. And which image? The image with index 1, this guy, same thing, okay? All right. Let me show this picture, and then, yeah, that's it. This is the image, okay? So as you see, the first ones are all black because, as you see, these are the corresponding. So again, go 8 by 8, okay? 1, 2, 3, 4, 5, 6, 7, 8. Just focus on this first 8 because this is 8 by 8. 8, then the second 8, then 7, 8. Look at the one, the first one, second one, and third one are all 0. That's why you see black. And then 12 out of 16 is a gray value. If you see 16, those are the ones that are corresponding to all white ones, okay? So this is digit 1, as you see. As you see, this is a distorted image because this is not the original image. Original image is 64 by 64. Values are changing from 0 to 255. All right, so this is our data set. Now let's train this model for linear SVC, which we don't know now. We're going to learn about it. It is a linear support vector machine. We're going to learn about it later, okay? It's a linear classification algorithm. For now, let's just just know this much, that this is a linear classification. It's a classification because I have 10 different categories, and I want to classify any new data point into one of these categories, okay? So for that, I'm going to, first of all, import my model, my classifier. So this classifier is kept at scikit-learn under SVM library. Okay, SVM is holding all these different classifiers for support vector machines. I'm going to import, sorry, I'm going to be importing, this is my classifier, linear SVC, okay? This is the first step. This is, I imported it, okay? Second, let's instantiate. I just put these steps here so that we go step by step. Let's instantiate an instance from this model. It's very simple. Later on, you'll see we are going to add some parameters, but for now, we are going with really basics. I'm just going to instantiate my algorithm. Okay, so what is this? This is a class. This is an instance, an object, which is inheriting all the attributes and methods of this class. So SVM now is an object that I can fit, I can predict with, and I can test the score. Okay, I can dot score. So it comes with all these methods that linear SVC is providing. So I instantiated this. For now, I'm not setting any parameters. It's later on we can work on it. Okay, so SVM is one object from that class. Now I'm ready to fit my model. So I will fit my model on my trained data set. Remember, SVM comes with fit method. So fit, I'm gonna be fitting my model on my trained data set that I created earlier, xtrain. Okay, let's do it. xtrain. Of course, when we are fitting, because this is a supervised model, and then I need the corresponding target variable, right? Sometimes I go blank. Okay, so this is my fit model. It's gonna give some warnings, because for convergence, it says increase number of iterations. Number of iterations, one of the parameters of linear SVC, which I didn't set it now, so don't worry about it. Okay, so I fit my model. Next, I'm gonna make the prediction, and I'm gonna evaluate my model. So first of all, let me make my prediction. Let's call this y hat. Okay, let's call it y hat. Let's use this one. Okay, now I'm using SVM. Now SVM, I'm still SVM, but this SVM is different than this SVM now. This SVM is now trained. Okay, something happened in between these two steps. At step 3, SVM is trained. So this SVM now knows the model parameters. Now knows it's a trained model. So I'm gonna be using this trained model to predict target values for my test data set. Now, I already know my target values. I already know my true target values for test data set, Y test. I already know that. But I just want to test how well my predictions are. Okay, that's why I first predict my target values for this data set, and I call it Y hat. Okay, so let me, I'm looking at my notes, actually, because it's really hard to, sometimes you go blank, you don't see what mistake you're doing. I don't want to waste your time. So that's why I'm looking at my notes and I'm typing the code. Okay, so let me print my Y hat. It's not gonna print the whole thing, it's gonna print some of them. So, and then let me print my true labels. Okay. This is my whole Y hat, it printed everything. Okay, and then this is my this is my train. So let's see. I just printed the I'm printing different things. Okay, so this is my Y hat for X test. This is my true Y test value. As you see, I predicted, let's make this a little bit longer. As you see, I predicted some of them correctly and some of them incorrectly. See, in my test data set, I couldn't predict some of them correctly. Let me do the same thing on my trained data set. I just want to show you the difference between. So most likely my trained data set will do a much better job. Y hat train, okay? I'm predicting my trained data set. Because I already trained my model on my trained data set, my predictions, of course, will come better on my trained data set. Okay, let's now look at this. You see, so the first two are test data set. The other one is, this is predicted train data set. This is the true train. So as you see, I don't have any misclassified training data points, but I have some misclassified test data points. Okay, because my model is fitting in this case, as much as I can see, fit perfectly to my train data set, and it's making some mistakes on my test data set. All right. So if you like, you can even get the score, okay? SVM. Now I'm still using the same SVM. Get the score on your test. Let's do this. Test accuracy is, remember this is the placeholder. This is formats. Let's do the same thing for train data set, just to see how well we are doing. Okay. You see, our train accuracy is 99%, test accuracy is 94%. So this is a good indication of overfitting. So you might try to tune up your model for this linear classification. I don't know how well you can tune it up, but you can try to tune up your model to reduce your train accuracy, but increase your test accuracy. Okay. All right, I have to stop, guys. I have another meeting that I have to attend, so I have to stop. What we can do is next time, before the next session's lecture, I will continue from here. Okay, I'll continue from here so that we can practice grid search and cross validation, and then I'll start with my lecture next time. Okay, I will also post the assignment. I just need to add one or two things, and don't miss the assignment hour with the other instructor. I think it's gonna be on Saturday, but they're gonna let you know. So it's gonna be helpful for you. Okay, thank you for attending, and I'll see you next week. Continue from where we left. Okay, thank you, bye.